Okay, so welcome everyone after this break, and it is my great pleasure to introduce Clifford Gilmore from University of Manchester. He will be talking about the dynamics of weighted composition operators on Fock spaces. So please.
Okay, thank you very much. And thank you very much to you and the other organizers for the opportunity to speak at this very nice focus program. So as the title suggests, I'm going to be talking about the dynamics of weighted composition operators on Fock spaces. And this work was done while I was a postdoc at University College Cork, which is why I need to mention my sponsors, okay? So this was done with Tom Carroll, and if you'd like to know more after the talk, then you can find all the details in the article. Okay, so of course, it's necessary to define the notation and to remind you of what a Fock space is. So here we have P in this range, and for alpha greater than 0, we have that the Fock space, so this F alpha P, so this contains the entire function such that this norm here is finite. So if you are familiar with function spaces, which I am sure you all are, some parts of this will look quite familiar. So it's a P norm, so you have the P appearing here, and the integral is taken in this case though over the entire plane. So here we need to have this Gaussian weight in order to, I guess, make this a sensible norm. The P also appears out here and in the Gaussian weight as well. And so the alpha here, it's kind of said to play the kind of role of Planck's constant in this theory. And why are Fock spaces interesting? So one reason is that quantum mechanics uses them to represent particle states. But of course, we're mathematicians, so we're interested in them for their own right as well. So one of these Fock spaces, so excuse me, F alpha 2. So this is a reproducing kernel Hilbert space, and the inner product is given by this integral here. And you may have seen this in other contexts called the Segal-Bargmann space. So if you've seen that called the Segal-Bargmann space, this is depending on your terminology. Some people say Fock, some people say Segal-Bargmann. And the reproducing kernel is given by this function here. And well, I guess that's kind of it in terms of setting up the Fock spaces. But just to give you your bearings for the kind of functions that live in Fock spaces. So if we consider the function fz equal to e to the bz squared, so this is in f alpha p if and only if mod b is less than alpha over 2. So this is just to give you an idea of the type of functions that live in these Fock spaces. So of course, there is a version of the Fock space, which is given by a kind of a subnorm. So this F alpha infinity, and it generalizes to this using this subnorm in exactly the way you'd expect. But one thing to note here again is that we have this Gaussian weight involved in the subnorm of the any function f from the Fock space. And here, the difference between the f infinity space and fp for p less than infinity is before we had this function is in the Fock space if this inequality was strict, but for f infinity, this can be less than or equal to here. Okay. And then one other space that's of interest to us today, which I will call cheekily, I'm not sure if it's standard terminology, but I'll call this cheekily the little Fock space. So this is given by, so it's the closed-out space of the f infinity space. And so it's given by functions f such that this limit is equal to 0. So again, here you can see this kind of Gaussian weight appearing in the term. So this little Fock space is the closure of the polynomials in F infinity. And why this is interesting to us today is because this is separable, whereas F infinity is non-separable. So more about that later. And here, again, just to get your bearings for the type of functions that live in this space. So if we have this function f here, so this is in the little Fock space, if and only if this inequality here holds. So, and again, you can see that this is strict. So we go revert back to the the behavior of the p less than infinity case. So the operators that we're interested in today in terms of what's happening in the Fock space setting are weighted composition operators. But before we get to weighted composition operators, I'll just remind you of what I'm sure you've all seen are composition operators. So we'll just let this script f here denote all of these different spaces here, just to kind of shorten the notation. So the composition operator, so C phi with symbol phi, so is defined as follows. So it has a composition here, so F is composed with phi. So this works out as follows. So C phi of F at Z is equal to F phi, F phi of Z, where Z is complex number. And then this is generalized to weighted composition operators as follows. So we have a symbol phi again, but now we also have a multiplier phi. So the weighted composition operator has this multiplier on the left here, and then we have the usual composition here. So this works out as W psi phi of F at Z. So this is equal to psi of Z F phi of Z. So they're the operators that we're kind of interested in today. So before we talk about any dynamics or anything like that, it's probably important to also mention the kind of properties that make these excuse me, weighted composition operators bounded or compact or other things like that. So in order to do this, we need these two quantities here. So basically, if we have entire functions psi and phi, then this kind of is what we work out here as mz is mod psi squared with this kind of exponential term here, and then m psi phi. So excuse me. This is the supremum taken over all of these mz's. So this was used by Lee and Hai and Koi in order to characterize when the weighted composition operator is bounded on the Fock spaces. And what they showed is that the weighted composition operator is bounded on F if and only if the following holds. So if and only if the multiplier psi is an element of the space, and also we require that m psi phi is finite. Okay, so this is a complete characterization of the bounded weighted composition operators acting on the Fock space. So something else to note here, and it was shown by Lee, is when this holds, then it turns out that our symbol phi is of the following form. It's of the form A plus lambda z, where mod lambda is less than or equal to 1. So that would be useful for us later in the talk. So that is the case when the composition operator is bounded. So now the next thing is to maybe have a look at when the weighted composition operator is compact. So the complete characterization was given by these authors here. And what they showed is that the weighted composition operator is compact on F if and only if our symbol psi z is equal to A plus lambda z, where mod lambda is less than 1. And we also require that the limit of mz of psi phi is equal to 0 as z goes to infinity. So again, this is a complete characterization of when the weighted composition operator is compact. And that's all very neat and very nice results that have been shown by all these authors. So then that we have the space, Fock space. Now we have the operator, the weighted composition operators. We've looked at them, and now we'll look at what we mean by the dynamics of the operators. So here, what we mean is we have the weighted composition operator, and we're going to look at the kind of long-term evolution of the iterates of that. So this is normally what we look at when we're looking at dynamical systems. So if we just think about X as a general separable interdimensional Hilbert harmonic space, then we say that like T, and we consider T is a bounded linear operator. And then we use this notation T to the n to mean n-fold iteration of T. So the phenomenon that we're interested in linear dynamics is hypercyclicity. And we say that T is a hypercyclic operator. So if there exists a vector X in our space such that its T orbit is dense, so we take all the iterates here, so X, T, T squared of X, and so on. And if this is dense, then this gives that the operator is hypercyclic. And we also say that the vector that makes T hypercyclic is a hypercyclic vector for T. So there's also, excuse me, there's also a weaker notion, which is known as supercyclicity. So the definition is quite similar to hypercyclicity. We start off by requiring that we have a vector X in our space, but this time we look at the projective orbit. So we're allowed to multiply by scalars here in the orbit. And such an X is called a supercyclic vector for T. And of course, we have that hypercyclicity implies supercyclicity. So the first kind of observation that we can make here is that our F infinity space is non-separable. So this doesn't allow us to think about hypercyclicity. Hypercyclicity is a requirement, or separability is a requirement for hypercyclicity. So here we're interested in the dynamics on these spaces. So P in this range or in the little Fock space. And before we talk about the Fock space, you might also wonder for other function spaces, what kind of dynamics do we have? So I'll just mention briefly a very elegant result here by Bourdon and Shapiro. And they gave the characterization of, so the composition operator is hypercyclic on the Hardy space on the disk here, if and only if the symbol is an automorphism of the disk and it has no fixed point in D. So very neat and nice characterization there of when composition operators are hypercyclic on the Hardy space. So I guess in order to approach this problem, we can consider kind of different cases. So we have that the symbol phi of z is given by a plus lambda z, where mod lambda is less than or equal to 1. So we know that from the work of Lee. So the first thing we can consider is, what about the case when mod lambda is equal to 1? So in this case, we know that the symbol is of this form. And actually, Lee also showed that we can get an explicit kind of representation, an explicit kind of statement here of the multiplier psi. So it's of this form. And what Lee also showed is that when mod lambda is 1, then this is a normal operator. Sorry, I have a bit of a head cold. I hope it's not bothering you too much. So that this operator is normal on the Hilbert space, the Hilbert Fock space, and by a well-known result in linear dynamics. So we know that normal operators cannot be supercyclic. So the question now is to ask, what about the case mod lambda equal to 1 for p different from 2? But we were actually able to show, Tom and I, that for a weighted composition operator, so we let it to be a bounded weighted composition operator, and we consider the symbol phi here with mod lambda equal to 1, then it turns out that the weighted composition operator is a constant multiple of an isometry. And a corollary of this then is that this operator cannot be supercyclic on these spaces. So that means we're basically, for mod lambda equal to 1, we've completely ruled out any interesting linear dynamics. So in order to tackle the case when mod lambda is less than 1, we'll first need to consider some of the kind of Banach space properties of Fock spaces. So we'll mention the duality. So kind of as you would expect with function spaces, if you've seen other function spaces. So we have that the dual space of f alpha p can be identified with f alpha q, where, as usual, these are conjugates. And this is done via this integral pairing here. And if we consider here the little Fock space, so the dual of this can be identified with f alpha 1. So when mod lambda is strictly less than 1, so the kind of two observations we can make straight away are, first, that if we consider the adjoint acting on these point evaluations, k of z here, then we have this identity. So the adjoint of a weighted composition operator acting on this point evaluation works out like this. Second observation is when mod lambda is less than 1, then this symbol here has a fixed point at this point. So this gives the following. It gives that the weighted composition operator, or the adjoint of the weighted composition operator, has an eigenvalue. Excuse me. So by another well-known result in linear dynamics, we have that basically we require that the adjoint of a hypercyclic operator has empty point spectrum. So in this case here, we can immediately rule out hypercyclicity in the case mod lambda less than 1. And another property that we have from linear dynamics actually is that if the weighted composition operator is compact, it can't be supercyclic when the adjoint has an eigenvalue. So this rules out quite a lot of cases in terms of interesting linear dynamics. So the question now is what's left? So what we need is a weighted composition operator with mod lambda less than 1, which is bounded but non-compact. So this kind of project started out, first of all, wondering about the linear dynamics of weighted composition operators, but it required us then to go deep into the kind of properties of weighted composition operators acting on Fock spaces. So here, we need to consider the case mod lambda less than 1 for weighted composition operators bounded but not compact. So what we did in order to investigate this was we considered the kind of fundamental properties of order and type of entire functions. So this is something that I'm sure you all know from complex analysis. But just to remind you, if we have a function f of z equal to e to the a z squared, then we have here that the order rho is equal to 2, and the type sigma here is equal to the absolute value of A. So the first kind of result in this direction that we got was if we consider the symbol with mod lambda less than 1, and if we consider the multiplier with order strictly less than 2, or if it has order 2 and type strictly less than alpha beta over 2, where we've used beta as shorthand for this quantity here, then our weighted composition operator is compact on the Fock space. Then we also show that if the multiplier is order greater than 2, or if it has order equal to 2 and type strictly greater than alpha beta over 2, then this operator is not even bounded. So this allowed us then to use the Hadamard factorization theorem to show that so if we have a weighted composition operator, so it's compact if and only if the multiplier is of the form this. So psi of z equal to this exponential here, and that mod A2 is less than alpha beta over 2. So this was the kind of way to get an explicit kind of characterization of when the weighted composition operators are compact by looking at the multiplier. So this kind of complements the other characterizations that were given by the other authors that I mentioned earlier. And then this is the case that we're interested in when it comes to linear dynamics. So this weighted composition operator is bounded but not compact if and only if our multiplier is of this form here, with mod A2 equal to alpha beta over 2, and either one of these slightly technical conditions holds. So here again, we have an explicit way of, identifying when a weighted composition operator is bounded and not compact. In this case, mod lambda less than 1. So this is the only hope that we have when it comes to finding a supercyclic weighted composition operator on the Fock spaces. So what's left? So we have our symbol of this form with mod lambda in this range here. We have our multiplier of this form where we have this condition on A2. So, excuse me. So we again had to break this down into different cases. So we had different cases depending on whether lambda is real and p is infinity. So the approach that we took to here was to show explicitly that the projective orbit of the weighted composition operator is not dense. So the second case here is lambda is a real number again, but p is finite. And here, what we were able to use was this necessary condition known as the angle criterion. So we have that W psi phi fails the angle criterion. And the third case here, when lambda is purely complex, what we showed was that so W squared, so W psi phi, excuse me. So W psi phi is raised twice here. So this turns out to be a compact weighted composition operator. And then we were able to use a very nice result by Ansari, which showed that powers of a supercyclic operator are supercyclic with the same supercyclic vectors. So this basically, all of these three cases here combined lead then to this kind of final theorem. So the final theorem being that if we have a weighted composition operator here acting on any of these Fock spaces, then it cannot be supercyclic. So that was the kind of end of the journey. it took us to kind of unexpected places in terms of digging deep into the properties of Fock spaces. But yeah, it was very interesting, and these are the references if you'd like to read up more. And thank you very much for your attention. And sorry about my head cold and my coughing.
Thank you, Cliff, for this beautiful talk. So, is there any question or comments for Cliff?
Okay, so I have a question. If I understand correctly, the central fact is that you have a characterization of the Fock space in terms of the order and the type of your entire functions. So
yeah, go on, sorry.
Yeah, so can you do the same kind of result, changing the order and the type? So
how do you mean by changing?
You change the space, you don't take the Fock space, and you just look at entire function with a certain kind of type and order.
And in order to get a kind of a characterization of the kind of functions that live in the space, is that what you're asking about?
No. So can you do the same thing about the supercyclicity or hypercyclicity?
Right. So, excuse me. I guess, like for other spaces, you consider the composition operators or the weighted composition operators. And yeah, I don't know off the top of my head if there is a characterization in terms of the order and the type of the kind of multiplier or the symbol that make the composition operator. But in terms of linear dynamics, I think that's like an interesting question. All right. It'd be probably something that would be worth investigating. I mean, we already have very nice characterizations, for example, the Bourdon-Shapiro result on the Hardy space. But yeah, it could be possible. Yeah, it's a nice idea. Could be worth exploring. Thanks.
Thank you.
Okay, so I have just one quick question. So is there a characterization of isometric, weighted composition operators on these Fock spaces?
Yeah, so I think if you look at the work of Lee, he considers this question. So.
Okay, but okay. Thank you.
Okay, I have also one question. Thanks, Cliff, for your talk. Hi. I'm just wondering if there is some recurrent composition operator or not. You show that there is no supercyclic or hypercyclic. What about recurrence?
Recurrence in what sense?
You know that vector x is recurrent if there exists some crescent sequence of integer nk, such that t and k of x goes to x, and we assume that the set of recurrence vector is dense.
Yeah. So I don't know of any work done on that, but I think it would be a very interesting question to ask.
Okay. Okay, thank you.
Thank you.
Is there any other question or comments? If not, let's thank Cliff once again.